Hey everyone, in this video we're going to talk about section 4.3a, which is about real zeros of polynomial functions. We're specifically going to be looking at the tie-ins between the zeros and the function itself, and we're going to talk about how do I go from something that is in standard form, especially when it's not a quadratic or a cubic that we can easily factor, and get it into factored form. So starting us off to talk about this process, we're going to talk about long division, okay? And so we're going to review just normal integer long division. So let's say that I have, 125, and I wanted to divide it by 3. A little bit of vocab. The 125 is going to be called the dividend, because that's what's being divided. And then the 3 is going to be called the divisor, because that is what is doing the dividing. So if we were going to do long division, and just do this anywhere on your paper, but I'm going to set up the 3 and then the 125 underneath the division box. So if you kind of recall back to, I don't know when you learned this, 4th grade, the process of long division kind of goes like this. So I'm looking at that 1, I'm thinking, okay, how many times does 3 divide into 1? Well, it doesn't. So we have to look more broadly at this. I'm going to think, okay, how many times does 3 divide into 12? Well, good news for us, it divides in 4 times. And so then we take the 3 and we multiply it by the 4 and we get 12. We line everything up. After that, we go ahead and we're going to subtract that. So 12 divided by 12 is 0, and we bring down our 5. And now we start that process over again. So I think, okay, how many times does 3 divide into 5? And it divides into it 1 time. So then I'll take 1, I'll multiply it by 3, then I'm going to subtract my results. So 5 minus 3 is, 2. Okay, and then we repeat the process. We think, okay, how many times does 3 divide into 2? Well, it doesn't, not evenly at least. So we would say that 2 here is our remainder. Okay, because that's all we have left over. So because our remainder is not 0 and it's a different number, I know that 3 does not evenly divide into 125. The 41 that we have up here is going to be called our quotient. Okay, so there's a few different ways that we can write our answers. The first way is in this format, which is going to be called polynomial form. Okay, so if I were to write my answer to this in polynomial form, I would say that, I'm trying to find a good spot to write this, sorry everyone. I would say, I'm going to come up here, that 125, my dividend, is equal to my divisor times my quotient, so 3 times 41, and then I'm going to add on my remainder, so plus 2. So this form here is our polynomial form. We can also write this in fraction form, okay? And so this would look like 125 divided by 3 is equal to my quotient, which is 41, plus my remainder over my divisor, so plus 2/3. And that is my fraction form. So this process of long division that we can do with integers also extends to what long division could look like with polynomials, okay? So in example 1, we're going to use long division to find the quotient and the remainder when f of x is divided by d of x. And we're going to write our summary statement in both polynomial and fraction form. Okay, so basically what we are trying to do is I am trying to divide 4x cubed minus 8x squared plus 2x minus 1 by x plus 3. Okay, and I'm trying to figure out what does that equal. Well, we're going to start this process with some polynomial long division. So I know that x plus 3 is my divisor, and then the cubic polynomial is going to be my dividend. So we have 4x cubed minus 8x squared plus 21 minus x. Okay, so starting off this process with polynomial long division, I know that I have this x plus 3 that's doing the dividing. I'm only going to take a look at that x term first, okay, so like our leading term. And I'm going to think, okay, how many times does x divide into 4x cubed? Well, sometimes thinking about it that way is a little bit difficult. Hold on, I'm noticing that I wrote this a little bit off, so I'm going to fix that first. This was, hopefully you caught that, 4x cubed. Wow, I didn't do a very good job. 4x cubed minus 8x squared plus 2x minus 1. There we go. Okay, Actually, before I go on, one thing about polynomial long division that we want to keep in mind is I want to make sure that I have all of my terms going in, that I have my polynomial written in standard form, so least to greatest, or greatest to least with our exponents, and I want to make sure that any missing terms are filled in. So here I have a cubic term, I have my quadratic term, my linear term, and then my constant term. I'm not missing any terms. Let's say, for instance, that I was missing the x term. I would want to write in 0x, so you do want to have all of your placeholders in there. Okay, back to where we were though. So when I'm going into this and I'm thinking, okay, well, what does it divide into? I almost like to kind of flip that and think, what do I need to multiply my x by to get 4x cubed? Well, I know I need to multiply that by 4x squared. I like to kind of line up my terms together, like my x squared over my x squared. It doesn't really matter though. So now what we're going to do is I'm going to take my 4x squared and I'm going to multiply it by both the x and I'm going to multiply it by my constant of 3. So 4x squared times x is 4x cubed. Okay, so I'm going to line up my cube terms. And then 3 times 4x squared is going to be 12x squared. And I'm going to line that up with my x squared term. Okay, so now if I'm going back to my integer long division, we went ahead and subtracted that 12. So I'm going to subtract or change the sign on both of my terms that I had here. So both of those were positive, changing my sign is going to make them both negative. Now I'm going to do my subtraction. So good news for us is our cubic terms end up subtracting out, and so now I'm going to have negative 20x squared left over. I'm also going to go ahead and I'm going to bring down my other two terms. So I'm going to bring down my 2x, and I'm going to bring down my negative 1. And so now I'm going to repeat that process again. So I'm going to look at my negative 20x squared and think, what do I need to multiply my x by to get me negative 20x squared? Well, I need to multiply that by negative 20x. And so now I'm going to multiply my x, and I'm going to multiply my 3 by that term that I had. So I'll have negative 20x squared. And then multiplying 3 by negative 20x will give me negative 60x. Okay, drawing my line, I'm going to go ahead and subtract these terms, and so that's going to be changing my sign. So my negative 20x squared will become positive. My negative 60x will become positive as well. So my x squared terms are going to divide, or are going to add to 0. And so now I will have 62x, and then I'm going to bring down my 1. And I'm going to continue this process again. So I'm going to have 62x here. And I'm going to think, okay, what do I need to multiply my x by to get me 62x? Well, I need to multiply that by positive 62. So multiplying that by each of these terms here, I'm going to have 62 times x. And then 3 times 62 is 186, I believe. All right, so going ahead, draw my line. I'm going to subtract both of those terms. So that changes the sign on both. So my x's end up dividing or adding out, and then I'll have negative 187. Okay, if I continued this process again, I think, okay, what do I need to multiply x by to get me negative 187? Well, I've run out of x's, so there's nothing else that I can multiply this by that's not going to turn it into some sort of rational function. So in this case, the negative 187 is going to be our remainder. So a couple different ways that we're going to write our answer. So first, if I were going to write this in fraction form, I would say that my 4x cubed minus 8x squared plus 2x minus 1 divided by x plus 3 is equal to, that's going to be my quotient, so that is what I have up here. So 4x squared minus 20x plus 62, and then I'm going to add on my remainder divided by my divisor. So plus negative 187 over x plus 3. So there is my fraction form. All right, if I wanted to write this in polynomial form, this would look like my function 4x cubed minus 8x squared plus 2x minus 1. And that is going to be equal to, running out of room, I did not do a very good job writing this. That's going to be equal to my divisor times my quotient, so x plus 3 times 4x squared minus 20x plus 62. And then we would need to go ahead and add on our remainder, so minus 187. And so that's our polynomial form. So either way is fine. I can see that polynomial form looks like it's going to be a polynomial because I have these two polynomials here, and then I of course have on this this other number that we're subtracting out so we can get our constant term to be what we want. So I encourage you to go ahead and, if you want to, multiply this out and then subtract the 187, and we should get back to the original polynomial, our f of x that we had to begin with. Okay, so polynomial long division is going to be really helpful for us to be able to eventually factor this. You might be familiar with synthetic division from Algebra 2, okay? So we can use synthetic division to accomplish the same thing. However, there is like a but, okay? We can only use synthetic division when we are dividing by like a linear binomial, when we're dividing, when our divisor is linear. Okay, so what I mean by that is our divisor, like our x plus 3 up here, is linear, so I can go ahead and I can use synthetic division for this. And so that's what we're going to do in example 2. Okay, we're going to use synthetic division to divide f of x by d of x using our functions above, and we're going to write our answer in fraction form. Okay, so when we use synthetic division, I have my x plus 3, that is my dividing term. We go ahead and we always start by finding our k value. So our k value is going to be the value of x when this is set equal to 0. Well, so that means that x is going to be equal to negative 3, so our k value is going to be equal to negative 3. So when we use synthetic division, I'm going to have my negative 3, I'm going to put it in this box up here, and then we are going to list out the coefficients from our dividend polynomial up above. So what that means is this is our dividend here. I'm going to list out those coefficients, and if I have a 0, I'm going to make sure that I put in my placeholder. So I have a 4 as my leading coefficient, negative 8 as my next coefficient, my 2 is my linear term, my negative 1 is my constant, okay? Again, if I had any missing places, I'd put in a 0. Okay, so using synthetic division, we're going to go ahead and we're going to bring down that leading coefficient, and I'm going to place it underneath here, okay? So now I'm going to take that number, and I'm going to multiply it by my k value. So 4 times negative 3 is negative 12, and I'm going to place it underneath here. Now, the key difference between using synthetic division and long division is from here, we're just going to go ahead and straight up add our terms. We do not need to subtract. We do not need to change any signs. Okay, so negative 8 minus 12 is going to give me negative 20. Now I'm going to repeat my process. I'm going to take that negative 20, I'm going to multiply it by my k value of negative 3, and so I'm going to get positive 60. Now I'm going to add those terms together, so that's going to give me 62, and then I'm going to continue on. So 62 times negative 3 is going to give me negative 186, and then if I add those terms together, that's going to give me negative 187. So when I do synthetic division, this number that I end up with the end is going to be our remainder. Okay, and so the numbers that we have right now are going to be our terms reduced down by a power of 1. So like we started with a cubic term, and so now that number that we have right here has reduced down by 1 power, so this is going to be my quadratic term. So this is going to end up being 4x squared minus negative 20x plus 62. And then my remainder, if I write this in fraction form, I'm going to have minus 187 over our divisor, x plus 3. And I do see that that's what we had from up above. So our two forms are consistent. All right. So we've spent all of our time so far talking about long division, synthetic division. Why are we doing this? Well, and we're just going to go ahead. We're going to skip over example 3 for right now. Okay. Well, the reason that we're doing all of this is we're eventually going to be trying to learn how to factorize our polynomial especially when it's not a normal quadratic or it's not a cubic, and we want to try to get it into factored form so we can find those zeros. Okay, so starting off, we're going to look at some different theorems that are going to help us eventually get there. Okay, so the first theorem we're looking at is the remainder theorem. So remainder theorem says that f of k is the remainder of the quotient f of x divided by x minus k. Let's go ahead, we're going to use synthetic division to determine this, and then we're going to talk about what is this remainder theorem really telling us. So in this example, we're going to use the remainder theorem to determine the remainder when f of x is divided by x minus k, when f of x is equal to 2x cubed minus 3x squared plus 4x minus 7, and k is equal to 2. Okay, really what this is saying is that we are taking our polynomial, 2x cubed plus 3x squared plus 4x minus 7, and we are dividing by x minus 2. Okay, we could use long division, we could use synthetic division, it's kind of our choice. I say that since we have a linear term down here, I think synthetic division is going to be the easier route. So x minus 2, I know that my k value is 2, so I'm going to go ahead and set this up. So 2, and then using my coefficients out in front, I'm going to have 2, that's my x cubed term, 3 is my x squared term, 4 is my linear term, and then negative 7 is my constant. Okay, so bringing down my 2, I'm going to have 2 times 2 is 4. Adding those together gives me 7. 7 times 2 is 14. Adding those together is 18. 18 times 2, let's see, what am I doing? Oh, okay, hold on. Hopefully you see the mistake that I made. I'm not restarting this video. Looking at our polynomial, and this is because it's written really weird, that's 2x cubed minus the 3x squared term, so that should be a minus. So let's go ahead, we're going to fix that. Okay, so negative 3 plus 4 was 1. 1 times 2 was 2. There we go. 4 plus 2 was 6. 6 times 2 was 12, and then negative 7 plus 12 is 5. Let me get that 2 there. Ooh, okay. So we did all of this. So what this is saying, I know that my resulting polynomial when we divided that was 2x squared plus x plus 6, okay? And we had a remainder of 5. So what remainder theorem is telling us is that f of k is equal to the remainder of the quotient. Well, if my k value is 2, this is saying that f of 2 is equal to 5. Okay, and so what that's saying is that one of the points on f of x, our graph, is equal to 2, 5. So that's kind of cool. So we can use synthetic division, we can use polynomial long division to help us determine output values if we know input values. So instead of going ahead and plugging in 2 into our function, we can use synthetic division and figure out what that value of 2 evaluated would be. Kind of cool. So why do we care about that? Well, okay, that's going to lead us into factor theorem. So factor theorem says that x minus k is a factor of a polynomial of f of x if and only if f of k is equal to 0. So that means that we want k, 0, to be a point on our graph. And that should make sense because x minus k is going to be a factor if our output value is 0. Or it's going to be a factor if this value k is an x-intercept. Okay, so we're going to use factor theorem to determine if x minus 2 is a factor of x cubed minus 3x minus 2. The reason that this is so important is if I'm looking at this cubic, well, that's not something that I can easily factor. Okay, so by using factor theorem, we can determine if I could write this as x cubed minus 3x minus 2 equals x minus 2 times some other stuff that we're not really sure. Okay, but this is going to help us begin to factor this process. So let's go ahead, we'll use synthetic division to determine that. So again, x minus 2 is linear, so synthetic is going to be okay to do. So if we have x minus 2, that means that my k value is going to be positive 2. And so here we go. So x cubed has a coefficient of 1. I see that I don't have an x squared term, so I'm going to put in a placeholder of 0. Negative 3 is my linear term. And then negative 2 is my constant. So here we go. So bringing down my 1. 1 times 2 is 2. Adding those together gives me 2. 2 times 2 is 4. Adding that to negative 3 will be 1. And then 1 times 2 is 2. Added those together, that gives me 0. So I do have a remainder of 0. So what that means is that I have the point 2, 0 on my graph. And so if I have a point 2, 0 on my graph, that does mean that x minus 2 will be a factor. So this question would be yes, x minus 2 is a factor of x cubed minus 3x minus 2. Okay, so that means that what we had written up here is true. I know that x minus 2 is going to be one of the factors. I'm not really sure what this other stuff is right now, but that's something that we're going to talk about in a future lesson. Okay, right now, all we're concerned with the fact is, yeah, we know one of the factors. Okay, to end this video, we're going to talk about 4 different statements that are equivalent to polynomial functions. We've kind of been alluding to them with some of the other theorems, but we're going to bring it all together here. So first, if f of a is equal to 0, then x minus a is a factor of f of x. 2, the value x equals a is a 0 of f of x. 3, an x-intercept of f of x occurs at x equals a. And 4, the remainder when f of x is divided by x minus a is 0. I encourage you to go ahead and pause the video and to think about each of those statements and why all of them are true. Okay, they're all equivalent. So what that means is that if any of these statements are false, then the other 3 have to be false, because all of these are really the same statement, just worded in a different way. So again, pause the video if you need to. Think about the connections between all of them. And then we're going to end up with 2 examples that talk about building polynomials. Okay, so example 6, we're going to find the polynomial function with leading coefficient 2 that has the given degree in zeros. So this polynomial has a degree of 4, and then it has 4 zeros, negative 3, negative 1, 0, and 2.5. Okay, so first, if we go ahead and we start writing out our polynomial, I'm going to have f of x equals, okay, I have a leading coefficient of 2, and then writing all of my zeros. Sorry, everyone, my dog wants to leave the bedroom. Hold on. Pause. He heard food down in the kitchen and of course wants the food. Okay, anyways, where were we? Okay, so we have our leading coefficient here, and then we have our zeros. So those zeros are going to help us write our factors. So if I have a 0 of x minus, or if I have a 0 of negative 3, that means I have a factor of x plus 3. Okay, my negative 1 will give me a factor of x plus 1. My 0 will give me an x minus 0 factor. And then my 2.5 gives me an x minus 2.5 factor. Looking at all of these, so we have all 4 of our factors that come from our zeros. Let's make sure that our degree matches. So we have a degree of 4, and so that's going to help us determine if we need to have any multiplicity on any of these terms, okay? I don't know about you, okay, and I can't see you right now because you're at home watching this video, but I don't think that any of these terms need to have a multiplicity other than 1, okay? Because that degree of 4 tells us that from each of these 4 zeros, each of those 4 zeros has already a multiplicity of 1, right? 1, 1, 1, and 1. So adding all of those together gives us 4, so we're good to go from there. If we had like a degree of 5, we'd need a little bit more information so we could determine which one needs to have a different multiplicity. But we're good from here. So now that we have all of these, let's go ahead and we're going to write this in more of a standard factored form because there's a couple of weird things. So first, that x minus 0, we're going to just write this as x. And usually if we have an x factor, just a factor, not x minus anything, we'll write that up towards the front. So I'll have f of x equals 2x. Okay, and we usually just put that up towards the front so that way the x doesn't just get lost in the middle of it. Okay. The last thing that we're going to look at for this is that x minus 2.5. So we do not typically see any sort of decimals in our factors, so we just need to rewrite this term so it doesn't have a factor or a decimal in it. So if I'm looking at x minus 2.5, I know that that is also the same thing as x minus 5 over 2. Okay, and so if I were to multiply through by 2, that's going to help me clear out what that decimal would be. Okay, so that's going to be 2x minus 5. So I'm going to rewrite that x minus 2.5 as 2x minus 5. And there we go. There's our polynomial function that meets all of our criteria. Example 6 did not say if we need to leave it in factored form or if we need to put it in standard form. Since it didn't specify, I would leave it in factored form unless you're a real go-getter and you want to go ahead and multiply that through. But I'm good to just leave it like this. Okay, last example that we have, we're going to use only algebraic methods to find the cubic function that passes through the 4 points that are given. Okay, so a couple of things looking at these points, I see that 3 of them have an output of 0, right, or a y value of 0. So what does that mean about all of those points? Well, those points are going to be our zeros of our functions. So -2, 1, and 5 are zeros. Okay, I also know that since we're trying to find a cubic function, the cubic function should have 3 zeros. So if I write my polynomial right now with what I have f of x equals, I have x plus 2 as a factor, x minus 1 as a factor, and x minus 5 as a factor. Okay, you might be thinking, okay, we're good to go, let's circle it and move on. Not quite, okay? We also were told another point. Also, we don't have any sort of leading coefficient on our polynomial. Okay, and I want to make sure that my polynomial goes through this other point, -124. So, we've looked at this a little bit in class before, but we are going to use our other point to help us figure out what our leading coefficient needs to be. So we have an x value and we have a y value, so we're going to plug that into our corresponding parts in our function, and we're going to find a. So I know that 24 will be equal to a times -1 plus 2 times -1 minus 1 times -1 minus 5. So let's see. So I have 24 equals a. Let's see, -1 plus 2 is 1 times -2 times -6. So 24 is equal to a times, let's see, positive 12. And so dividing both sides by 12, a is going to be equal to 2. So that's our leading coefficient. So our polynomial that meets all of these, goes through all of these points will be f of x equals 2 times x plus 2 times x minus 1 times x minus 5. And I do know that's going to be cubic because the multiplicity on each of these terms is 1 for a grand total of a degree of 3. Okay, that's all I have for this video right now. Looking ahead, what we're going to do is we're going to apply some of our theorems that we looked at earlier on to be able to fully answer a question that we kind of started with. Okay, so how can we go from a higher order polynomial that's in standard form, how do we fully write it out into factored form so we can find all of those zeros? That's it for this video, so I will see you all later.